Welcome back, my dear students. As we are studying the properties of the fluid here, one very important properties of the fluid. Whole fluid mechanics, and not only in fluid mechanics, in heat transfer also in the thermodynamics sometimes also we are studying this property here. That property, it is always exist in all kinds of the fluids here. So what is that property? Very interesting property here. So what is that property? That property is called as the viscosity. So there are many ways of that defining of these properties are there here. So how the physically we are understanding this property, that is also a very important parameter, because many physical problems are solved by considering this property here. This is a very important properties in case of the fluid flow related problems here. So therefore, how to study this property here now? In case of the benchmark, the principle or problem, we will study this property here. So what is that benchmark principle here? So before going to this viscosity, there are two types of the viscosities are there here. One is, it is called as the dynamic viscosity here, dynamic viscosity, and another one is, it is called as the kinematic viscosity here. Two types of the viscosities. Dynamic viscosities, it is indicated by the letter mu, and kinematic viscosity, it is indicated by letter usually small p here, small p. So now we will study first dynamic viscosity. What do you mean by this here with the benchmark that problem? I will take one plate here. This is the plate here. Plate. As you know, if the plate is not there, the fluid is moving like this here. All the fluid particles are moving with the same velocity. That velocity is called as the free stream velocity. Here the plate is not there. Then all the fluid particles are moving with the same velocity. That velocity is called as the free stream velocity. Why? Because plate is not there. The surface effect of the plate, it is not there on the fluid particles. They are moving here. So when the plate is present, what happens? This one now, see here. So if I take, this is the x-axis along the length of the plate, I will take this is the x-axis here now. Perpendicular to the plate, if I take, this is the y direction here. So any one point, I will take, this is the one point here now, immediately on the surface of the plate here. So this is one point, I will take it here now, immediately on the surface of the plate here. What happens? The fluid particles which are on the surface of the plate, immediately on the surface of the plate, they are having very less velocity, or else it will be called as zero velocity. Means what? There will be existence of no slip condition. It is existence of here now no slip condition here now. No slip condition means the particles are not slipping, they are not moving, means they will be remains there only here now. So here that velocity of the particle in the x direction, usually it is notation u is the velocity here now. It is having velocity of this particle is zero, almost zero at this point. U is there, it is almost zero here. Then next what I will do in this study, so I will move vertically upward here now, at a small distance of what? At a small distance of dy like that. Small distance dou y, partial distance. It is a very small distance if I move vertically upward here now. Small distance if I move here, so that distance is dou y here. Dou y or a dy. A small distance if I move, definitely at this the upper point here, when it has the particles are having some velocity here now, some velocity here like this. That is the magnitude of that velocity, it is the direction of the velocity. It has some velocity. That velocity is called as u plus delta u, or else u. You call it as u here. That velocity they are having u here now. Next, again the same distance vertically, if I will move here, same distance dou y I will move here. Then next, the particles are having more velocity, u plus delta u here. Again, if I move this vertically, same distance dou y here, the particles are moving with u plus 2 delta u here. Like that, if I am moving vertically upward, the velocity of the fluid particle is increasing. How much it will increase? It will increase more than the free stream velocity? Plate is not there? No, not possible at all. So, somewhere at the point here, this u is there, it is almost is equal to the u infinity here. So, see here now, if I draw this line here now, this is called the velocity profile, as we have studied here. So what we can observe from this the diagram or experiment here now. Maybe these layers are not visible. So theoretically we are studying here now, but it is happening. Experimentally proved here now. So the different layers of the fluids are there here. This is one layer, this is one layer, this is one layer, this is one layer. These layers are there. These layers are moving with a different velocity. It is moving with the u, it is moving with the u plus du. Then again it is moving with the, here now, u plus 2 du. Again it is moving with the u plus 3 du. Like that, it is moving like this here. It is moving like this here. So therefore, different layers are moving with a different velocity. Experimentally it is observed that one layer is moving with the other velocity on the surfaces here now. There will be the existence of shear stress here. What is shear stress here now? This is a force it is acting on this surface area here. So therefore it is the shear stress. Force on this area, it is the shear stress. So experimentally it is found that the shear stress exists between these layers. They are moving with a different velocity. That shear stress is denoted by the tau. So this shear stress is proportional to the dou u divided by dou y. What is this dou u? Change of velocity here now. Du, delta u, 2 delta u. It is the change of velocity between the layers here now. So not like that only these layers are taken. Only upper layer and bottom layer also we can take it. Between these two there will be the difference, that height or length here now, and change of velocity is from here to here what it is there here. This is dou u by dou y. This dou u by dou y, this is called as the velocity gradient here now. It is called as the velocity gradient. Velocity gradient means the change of the velocity at a particular distance. When we are moving at a particular distance vertically, the velocity is changing. How much velocity is changing at a particular distance is called as the velocity gradient here. So this is also called as shear deformation here. This is also called as the shear deformation here. This is also called shear deformation. And also in another way, this is also it will also in under some books it will be called as rate of shear strain here. It is also called as the rate of shear strain. Also it will be called the rate of shear strain. So this du by dy or dou u by dou y, velocity gradient it is there. Experimentally it is found that shear stress is existing and it is directly proportional to the dou u divided by dou y. This dou u by dou y is called as the velocity gradient or else shear deformation or else rate of shear strain it will be called here. So now this proportionality constant it is there, we have to remove it, we have to equalize it here. So next if I remove this proportionality symbol, one constant will comes here now, that is tau is equal to mu into dou u divided divided by dou y here now. So this is the constant here now. Mu is the constant. This is called as the dynamic viscosity. Or sometimes it is also called as the viscosity coefficient or coefficient of viscosity. Sometimes it is called also. Sometimes it will be only called as a viscosity. If we call it is only viscosity, means it is a dynamic viscosity only here now. So therefore this dynamic viscosity constant, it is coming from the experiments here now. So that is called as the viscosity here. How to understand? This is very important, that the relation we are getting here now, where shear stress is directly proportional to the velocity gradient. Where the constant it is coming, proportionality constant, it is called as the dynamic viscosity or a viscosity here now. Very important relation what we are getting here in this case here. So next here, is there any unit is there for this here now? Yes, for the mu we can derive the unit for the mu here now. In SI we can derive the unit here now. So how we can derive the unit here? I will make mu is equal to this relation. Mu is equal to tau dou y I will take here into dou y here divided by dou u. So tau is what? It is a shear stress here, Newton per meter square in SI. So into what dou y. Dou y is nothing but it is a distance here now. And next one is dou u. Dou u was what? It is a velocity here now. It is a meter per second in the denominator. It is a second per meter. Second into meter here. If I write in the numerator like this here. So meter per that is second here. So it is meter per second. I will write like it. Or else we can write it here now. Second here and meter here. So I will cancel it here now. This meter will get cancelled here now. So what is the unit I am getting here now? Newton second per meter square here. So this Newton second per meter square is the unit of the viscosity in SI, dynamic viscosity here now. So next here, this unit, it is the Newton second per meter square. We can write in a different ways also here now. Newton per meter square is what here now? This is nothing but a Pascal here now. We can write here now Pascal second here. Also we can write the unit like this also. And as the Poisse is the scientist, he has given so much of contribution in this study of this viscosity. So therefore, by his name, we are calling one unit, that is called as the Poisse. Means viscosity, especially dynamic viscosity, we can call unit as a Poisse here. So 1 Poisse is equal to what here now? The 1 Poisse is equal to here. So Poisse is the smaller unit here now. The Poisse is a smaller unit than the 1 Newton second per, it is a meter square here now. So therefore 1 Newton second per meter square is equal to, it is a 10 Poisse. This is the unit conversion here now, Poisse and this one. Then how to prove it here? How to prove this? 1 Newton second per meter square is equal to 10 Poisse here now. We can prove here. So proving of this one. So next, so 1 Poisse is equal to, we know that here, we know that 1 Poisse is in CGS unit here. CGS. It is in CGS. So as we know, in case of the SI unit here, SI unit, the unit of this viscosity is Newton second per meter square here. In case of the CGS, this force, how this is measured in force in case of the CGS? It is in dyne here. So therefore, this is in CGS, means the Newton will be more measured in the dyne here. 1 dyne here, 1 dyne. Second will be same in CGS also, divided by, in place of meter square, it is a centimeter square here. So therefore, 1 Poisse here, 1 Poisse is equal to 1 dyne into second divided by centimeter square here. So what I will do here now? what I will do, what is my intention here, like this I want to convert. I want to convert this dyne to Newton. I want to convert this centimeter to meter here. What I will do here now, now I will stop here only. I will continue this same, the unit conversion in the next video lecture. Thank you very much.